Record. All right, so today is about two-dimensional balancing. So we've got our little square, and we're going to make it bounce around on all the sides, just like the Office episode. So we're going to essentially make this little TV thing happen. Oops. Let me get that. And what is this going to look like? It's going to be like, our version is going to look like this. It'll have a little rectangle, and it'll have our turtle be a box, and then it'll get some random starting position and just start bouncing around the walls as you would expect it to, bouncing off as it should each time. And then hopefully one day it's going to hit right in the corner, if only. And we'll have to wait and see. So we talked about how to do this. Let's just refresh our memories as to what we thought about last programming lecture, and then we'll go and implement it for real today. So here was our game plan. We're going to draw our screen boundaries, just like this. We're going to keep it as we did before with just the up and down bouncing ball. And so it's going to be a bounding square. That will be our little window, and it's going to be 400 by 400. And so like this coordinate is therefore like this is 0, 0 in the middle. This coordinate is negative 200, positive 200 for that corner of the square. This corner is positive 200 in the x and negative 200 in the y, right? So that's like the bounds of the square, kind of. And then we want to make a square in a random spot. So it needs to be like, make a square appear maybe here, or I don't know, could be anywhere, maybe here, maybe here. Just like when the program starts, pick a random spot for the square so it's different each time, and then give it a random direction. And maybe this arrow represents our direction. We remember how to represent directions inside of a computer now, two-dimensional directions. It's always involving an x offset and a y offset now. That lets you move two-dimensionally, which is awesome. And we're just going to keep doing that. It's going to be a loop. Just forever move in your current direction if you can. Dot, 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 until you hit a wall. If there's nothing in your way, just keep going in that direction. That is your current direction, which is just the same as the bouncing ball. It's just worry about changing x as well as y now. And if you hit a wall, we'll have to use some if statements to discover that for each wall. And if we hit that wall, we bounce. Bounce and change your direction to be some other kind of direction. And maybe it goes here and we see that we hit this wall now. And again, we have to change our current direction now to be more this way. And so that's how we want to move around. All right, so that was what we decided. And hopefully it's kind of coming back to how we did it. But let's go down into the low levels again of things before we get to implementing. So we're going to make the turtle the square. We can totally do that. We can change the turtle into a square. That's fine. And it's the coordinates of the turtle himself that we will be using. So like here is our square. Turtle's been changed into a square. And he has some xy coordinate where he is currently. And that's what we're going to be moving around to new xy coordinates as we draw each new frame. And we're going to store his direction, the square's direction. Maybe this is the direction that we want him to move in next. That can be broken down, remember, into an x offset and a y offset. So like go that way in the x before the next frame, go that way in the y before the next frame, and that will have caused you to slide diagonally. So we'll call that like x off for x offset, and this can be y off for y offset, something like that. And so every frame, we're going to move the turtle's x by the x offset and the turtle's y by the y offset. So like the new coordinate of the turtle after a frame is like, gets translated into like this. This it turns into x plus x offset, and then y plus y offset. Something like that. That's what it's going to end up as. That's how we'll move the turtle around. We'll just nudge him a little bit in that direction. And yeah, every direction has an associated xy offset. Like you want to, I don't know, just think about it. You want to go this way, positive x offset, positive y offset. You want to go this way, still positive x offset, but the y offset is bigger. This way, you have like a negative x offset and a positive y offset. This way, it's like negative x and negative y offset. And you can imagine that one's the same, but slightly different x and y negative offsets. This would be positive x offset, negative y offset. That's how you get it to move wherever you want. And so no matter what you would like, everywhere you could go has a certain pair of offsets. But I do want to say, though, that some offsets, maybe the direction's the same, but the amount is different, and that kind of has to do with the speed. So, like, imagine these two, like this direction and this arrow, maybe this is like go left 0.5 and up 0.5. That's the same as this direction. Let me try a better. That's the same as this direction, but maybe this offset is 1 and this offset is 1. See the difference there? So this is the same direction, but you move a little bit more, get nudged farther each time, but you're moving in the same direction. And so maybe it would be nice if we could always have a direction without being stretched. Or we should make our directions always have the same amount of nudginess, if that makes enough sense. So like, imagine a circle. Our direction should be radiuses of this circle. Like, if you're going to move this way, just like make sure that it's always length 1, that arrow. Make sure it's always length 1. If you're going to move this way, make sure it's length 1. Something like that. That's called normalization. That's going to help us because like this will move slower than this one, but it's the same direction. We'd like to just use a direction and not think about that size. So let's normalize it to always have, like, make sure that this is size 1. This arrow is size 1. It's going to move 1 unit in whatever direction it chooses. Okay? So that's kind of what I'd like. We'd like to normalize our directions. So are there any questions about that? And yeah, every direction has a way to be represented. Like if you want to go this way, go a little bit negative in your x, go a little bit positive in your y. There's always a right triangle somewhere. If you want to go this way, go negative in your y, positive in your x. Again, right triangle. Any questions about that? Do we remember how directions work? Two-dimensional ones. This normalization idea, though, I'm going to show you that. I'm going to show you what it means, and hopefully it'll make sense in code. But if we're good, I think I'm ready to go to code. So let me open up the original bouncing file, not the one with the gravity and all that. Let's just do the original one because we don't want to have gravity anyway. So this is like lecture 24's bounce. And let me figure out what lecture we're in right now. This is lecture 27. So I'll make a new folder for today. So save this as 2dbounce.py in a folder called lecture 27. 2dbounce.py, and we're going to start with what we had, just like we started with this when we were doing the gravity bouncing. Take most of this and change it up. So this is the code that we had before a while ago that just had the ball bounce up and down, constant speed. So that's what we're going to be changing now. So, okay, let's figure out what we want. Let's go to the turtle library documentation because we need to, I think the very first thing we want to do, right, was change the turtle to a square. A lot of this stuff we can keep, like keep the bounding rectangle, that's cool. Make the turtle not the ball, but the square. So let's figure out how to do that. Python turtle. And it was turtle.shape, I think. Turtle.shape, what could he be? We had him at circle right now. We've also used turtle before. We can make him a square. So simple as changing circle to square. That's not too hard. And the width is going to be the same. It all works out. So now he's a square bouncing, up and down only. So that's not bad. And so what did we do to move this turtle up and down? It was this x and y, turtle x, turtle y, kept track of where the turtle should be. And the x never changed. We just hard-coded it, or we made it some random value at the start, and then it just was always stuck at that x value. That never changed. But the y changed a little bit. The y changed a little bit. It started at the top, though, and it was being moved by this offset. It's the y offset. This offset was only for the y. It was moving down originally, and when we hit the wall, it became a positive offset to change the y upwards to make the ball bounce up until it, of course, hits the top wall then. We negate it all over again. But that is the part that needs to change here. So to get a direction that is two-dimensional, we would like two offsets. We were using just one for the y before. We need two now. All right, so that's what we'd like. And we need two offsets. So this was like a y offset. Let's change that everywhere. So this was turtle y offset. Global turtle y offset. Y offset. That's a better way to think about it. Change the y offset. Y offset. Y offset in the comment. I believe that's everywhere. So that was really, this was a better name for this variable. It was an offset to the y direction only, because we're going to need two now. So let's start that. And so it's still working out. I think we also wanted, oops, I guess I missed one, sorry. Where was that? Oh, sorry. There's two places in these where it happens. This is why we're checking it now. So that's just a new name for the variable, a better name for it, I think. And it looks like it's happy again. The other thing that we wanted was the turtle to start out in a random spot. So like anywhere. So that was up here. Make a square in a random location within the boundaries. So like between negative 200 and positive 200 for the x, between negative 200 and positive 200 for the y, something like that. Or maybe like 150, just something within it, so he's never outside. So that's, these were the starting coordinates for the turtle x. Like we gave him a random x. It's like make it between negative 150 and positive 150 now. And let's do the same for the y. No longer put it at the top, put it somewhere in the middle. So the y could be anywhere between negative 150 and positive 150. So now the turtle's going to start out in a new random spot each time. And so he's not going to be at the top anymore. So that was his random spot, down at the bottom left-ish area. So that's nice. That seems to be working. Run it again, it'll be random again. So that was the random spot for the turtle. But again, we're only messing with the y offset right now. That's all that we have. Any questions about it so far? All right, so yeah, to bring in two-dimensional motion, we need, and like arbitrary two-dimensional motion, what do we want? We want random x offsets and y offsets. So we would like to be able to move anywhere in any direction. So the x offset could be like negative, it could be positive. It's like move that way a little bit or that way a little bit each time. And then up or down, of course. And then the y offset could be, again, positive or negative. It's like, for this one, it was like move down and then right. For this one, it was move left and then up. Those are negative and positive x and y values. There could be any of those. So I think for our starting offsets, for like our y offset, we want it to be either positive or negative. So any random number. It could be any random number within some range, let's say. So we're going to have an x offset and a y offset now, though. That's going to be our starting random direction. All right, so this x offset and a y offset now. And so these two variables will together, these two variables together will form our direction. It'll be our random two-dimensional direction. And so we don't want to hard code these. We want them to be random because we want to maybe move up and right as well as down and left. And so we would like a random value between like -1 and +1 for each of these, because then it'll have a chance at being everything. And so we would like a random float, not a random int, because it's not really good enough. But if you're picking a random int between -1 and +1, it can only be -1, 0, and 1. There's not a lot of directions there. So instead of that, we can do real value distributions. We can say random.uniform, which gives you back a random value that's a float, floating point number, a float between your a and b. So like if you give -1 and +1, it'll make a float number. So like maybe 0.75, -0.3 between those numbers. And so that's what we want here, random.uniform instead of random.random. Random.uniform, maybe between -1 and +1. I'll use the 0.0 to signify, make it clear that it's going to be within that range. Floating point numbers. And so right now it's only the y offset that's being used in the rest of the program. We also want to have the x offset every frame affect the turtle's position. So every frame move the turtle's x coordinate and the y coordinate by that direction's amount. So change the x by the x offset and change the y by the y offset. Right now we're doing the y change already. That was just from before. We need to do the same for the x. Change it by x offset. Add it in there. That's our goal. And so change the turtle's y coordinate by the offset as well as the x. And so we might end up changing the x offset, so we have to declare that as global as well. And then we're also definitely going to change the global variable that is the turtle's x location now. And so that needs to be declared global as well because we're inside this function. And so that's that one. That's going to be our new draw frame. And yeah, so we want to change the turtle's y coordinate by the offset as well as the x coordinate. So turtle x, make it what it was before, plus turtle x offset. Isn't that nice? And so we'll keep, this is just the top and bottom wall checks. Not quite enough, but that's a good start. So all I've changed now was we added a random x offset, and we changed the y offset to be random as well. And so that'll make us point like left and up or down and right, whatever we'd like. And so that's going to give us a random two-dimensional direction, which we'll add into our current position each time we draw a new frame. So let me show you that happening. Whee! There it is, going left and down, and we have no x checking, and so he's going to fall off the page. Whee! So if we try again, it'll get a different random offset. Again, it's favoring to the right, but again, you can play this all day long, and it will pick a different one every time. So now it's going to the left. Again, we have no left and right wall checks, and so it'll fall off the page. Are there any questions about how we got to this? Just the introduction of an x offset in addition to our y offset and making it random gave us a random direction because we're going to change that each time by our offset amount because that'll move it from here to here. Any questions about that idea? All right, so let me show you an issue with this and we'll fix it. Let me say random.uniform between like -5 and +5. I'm going to try and highlight this issue where if it's a bunch of small numbers or a bunch of large numbers, the turtle's going to move faster if it's a bunch of large numbers versus a bunch of small numbers as your offsets. And that's maybe not what we want. So like if you get lucky, it's going to move super fast. Woo, super fast. Or if you just get some smaller numbers, the turtle will move slower. Like I think it moved even faster that time. You're at the mercy of the randomness. Like if it's a small number, like that one just shot off. If they are small, though, he'll move slower because that's a smaller amount to change each time. See, now it's small. Those were small offsets. We would like direction. We would like direction with a constant speed regardless. That's what we care about. So like if we randomly pick 0.5 and 0.5 or 1 and 1, let's normalize it so that it's always going to move the same speed in that direction. Does that make sense? That's what we'd really like. So regardless of which direction we pick, let's make sure that the turtle moves in the same speed in that direction. And so that's like force the arrow's length to be like a 1 or something, some constant amount no matter the direction. Because otherwise if it was like 0.25 and positive 0.25 will move even slower because it's random, but that's the same direction. We'd like to just move at a constant speed, please, turtle. That's what we want. So that is called normalization. Normalize the offset triangle because it's always a triangle formed by the offset, x and y. This arrow is really the hypotenuse of that triangle. The x offset and the y offset are the side lengths. We can just make it so that we can divide these x offsets and y offsets by the size of this hypotenuse to force it to be 1. So that's called a normalization process. And if you've taken physics or vector calculus, you will know what I'm talking about. And if you have not, one day you will get to that class, and this will all make sense. So what we'd like to do is let's normalize our direction so that it has a length 1 hypotenuse, always. I want to make sure these are unit vectors, it's the fancy term. So how do we do that? What is the hypotenuse of our random x and y offset triangle? Well, this is one's the x offset, one's the y offset, the length of this arrow, how fast it's going to move. That is our hypotenuse. We can do the Pythagorean theorem if we include the math library. Oops. So did I already include the math library? No. Import math. So this is like square root of a squared plus b squared. It's going to give us our hypotenuse. So direction, hypotenuse, length or something, that's equal to math dot square root x squared plus y squared. It's the x offset squared plus the y offset squared. That's going to give me the length of this hypotenuse. Maybe it's small, maybe it's large, regardless of its current direction. And if it is not 1, and it most likely will not be, let's make sure that it's 1. Let's change the x and y offsets to force this hypotenuse to be 1. And the way you do that is just divide the offsets by this length. That'll force the hypotenuse to be length 1 always. So turtle x offset, make it whatever it is, divided by this length. That'll force, once I do that to the y as well, that will force the hypotenuse to now be 1. So the direction is always move 1 unit in your arbitrary direction now, Mr. Turtle. So now, and you can confirm this with some math if you'd like. Now the length of the hypotenuse is guaranteed to be 1 in our direction. And that's going to make sure that no matter which random one I picked, we just care about the direction and not the speed. Now the speed's always 1 in whatever random direction we picked. And that is better. So now it's always going to move at that kind of speed that you see here. No matter which random direction it took, it's always going to move with that speed, that length 1 speed, rather than letting randomness pick the speed as well. We're letting the randomness only pick the direction. All right? So that might be a bit complicated, but that's at least what you got to do if you want that. Any questions about any of this code so far? So really I just added the x offset as well as the y offset. Did some fancy math to it to make it constant length each time, and just allow the x offset to change because now it's part of the direction, and we're off. And we have 2-dimensional movement. Any questions about any of that? Because really the last trick is getting it to bounce properly. Let's see here. So yeah, let's talk about bouncing. We talked about this last time. Let's make it precise. I said negative 200 and positive 200, but really I lied. It's negative 180 and positive 180 because you have to deal with the coordinates of the turtle are his center rather than his sides. So here is what happens. Here's when we know that the turtle has hit the wall. Let's see, I'll just redraw it. That's fine. So here's my bounding square. And here's 0, 0. 0, 0 is right in the middle. And it's a 400 by 400 square, which means like I said before, this is like negative 200, positive 200. It's that coordinate of that square. So when has the turtle hit the left and right walls? Because that's what we haven't really checked for yet. Technically, what we had before already does the right thing for the top and bottom walls. But let's generalize that. Let's understand why. This is like, when has the turtle hit the left wall? Well, it's when the x-coordinate of the turtle tries to go past or hits exactly this x equals negative 200 line. That's when he hits the left wall. But really it's relative to the turtle's center. And like here's the turtle hitting the left wall. This is his center, and his width was 40, if you remember that. Width and height is 40 for this currently sized turtle. So that means really, when is the turtle exactly touching the left wall? It's always relative to his center. What's his x-coordinate? It's when it's negative 180. See that? Because it's half the width. So negative 200 plus 20. So that's x equals negative 180. So that's when the turtle has hit the left wall. So if the turtle's x-coordinate is negative 180 or smaller, like we've shot him over here even farther if that's smaller, but that is when he's exactly touching the wall, when it's negative 180. Any smaller than that, he's outside the wall even. All right? So that's when he's hit the left wall. Same for the right wall. Now you know, right? If the turtle has hit the right wall, what does that mean about his x-coordinate? Because that's what you need to check. It means that it's not equal to positive 200, it's equal to positive 180 because it's relative to his center point. Right? And we've already done the right stuff for the y-coordinate. Similar fact is true about the top and the bottom. We've checked that already. Right? The turtle's hit the top wall. That means his y-coordinate, not the x anymore, is equal to or has exceeded positive 180. And same for down here. That means the turtle's y-coordinate, if he's hit the bottom or tried to go past the bottom, his y-coordinate is at most negative 180. See that? So those are the values we'd be checking for. So if you hit the left wall, that means your x-coordinate is less than or equal to negative 180. If you hit the right wall, your x-coordinate is greater than or equal to 180, and similar stuff for the y that we've already done. And now the question is, what do we do when we hit the side wall? Like, how do we bounce off? How are we supposed to bounce off? What are we supposed to do here? It involves negating just one of the offsets. So let me draw that for you. And we'll package this into a separate function as well. I'll show you that. So here's what needs to happen when we hit, let's say, the left wall. Because we need to bounce off, how do we do it? This might be too small. Let's see if I can resize it. Nice. All right, so here we are. Apparently, we're just hitting this wall right now. And why are we hitting the wall? That means our direction is moving us somewhere like this way. Because we're hitting the wall right now. Apparently, our direction is moving us that way. And how do we move that way? It's because we have a negative x offset, essentially. So our x offset is a negative value. Our y offset, at least in this drawing, is a positive value. So like move left and then up. How do we want to bounce off? Like if the box is coming in this way, we want to bounce off that way. Right? We want to make a perfect like 90 degree, like bounce right that way, something like that. Or relative to the center, it's like boop, boop. 90 degrees there. So that's the new direction that we want, and we have to build that from the old direction. So how do we do it? Let's see if I can draw it perfectly. We would like boop, boop. So this is the new direction that we want. Oh, this is like a 90 degree. What does that look like? How is it similar to the direction we came in on? Well, we still want to go up by the same amount in the y. See that? The y offset is not changing. That is the same y offset. But we now no longer want to move left in the x. We don't want to go negative. We want to go positive. We want to bounce off to the right and then up, rather than to the left and then up. You see that? But again, the length of this side down here is the same length. It's just move in the opposite direction. So this x offset, the new x offset, is the negation of your old one. You see that? That's going to be the trick. And that's the same for the right wall as well. So like if you're here and you're bouncing, like you came in this way, you want to bounce off this way, that means you had a positive x offset bringing you to the right. You want to bounce off to the left, which means you want a negative x offset now. See that? So again, negate whatever your current x offset is. And then same for the y. Same for the top and the bottom. If you hit the bottom, that means like you're coming in this way. And so you were going down and right, but now you want to bounce off that way, which means keep going right, but instead of going down, go up. So it's negate your y when you've hit a top or bottom wall. And it's negate your x when you've hit a left or right wall. Okay, any questions about that? You see how that's how we obtain the new direction from the old one. That's all we got to do. And so we've technically already done that for the top and bottom walls. It's like change the Y offset. That's all you needed to do. And so let's take this and let's move all the bounds checking, all this did we hit a wall checking stuff. Let's move that to a function. So instead of all this right here, it's just like what is draw frame, change your X and Y, and then like bounce if you hit a wall, bounce if hit wall. Just call it. That's easier to think about. And we'll just let that function do the rest. So if we hit a wall, bounce off. And we'll let this function deal with bouncing off the wall. That's nice. So def bounce if hit wall, what do we want to have happen? The rest of the stuff from before, which is going to involve changing all this stuff potentially. And we do want to keep this stuff. It's like, all right, if we hit the top wall or the bottom wall, we want to reverse our Y offset, make it negated. But if we hit a left or right wall, we want to reverse our X offset, negate that. And the first thing I want to tell you is there's a reason I'm using a bunch of separate ifs here. I guess technically you can't hit the top or the bottom wall at the same time, so you could have been like if, elif, totally fine. But it is very possible, and in the episode of The Office, you want it to happen. It's very possible to hit both the top and the right wall. Like when you hit the corner, that means you're hitting both walls at once. You see that? So you can't be like if, elif, 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 because you'll only ever handle hitting one of the walls, but you might end up hitting two. So like every corner is you hitting two walls, the top and the left, or the bottom and the right, something like that when you hit a corner. So you can't just use elifs. You want two separate maybe if elifs. I'll just make 4 separate ifs. It doesn't really matter. But it's possible to hit a top or bottom wall and a left or right wall at the same time. And so you can't like separate those things. It won't work otherwise. I hope that makes sense. Please yell at me if it does not. But let's see here. This is bottom and top. I guess we know we're in that function now. I don't need that comment anymore. We want to do the same thing for the left and right walls. So let's do left wall. So when do we hit the left wall? That is when the x coordinate is less than or equal to negative 180. So if turtle's x is less than or equal to 180, or negative 180, which is negative 200 plus the turtle width over 2. That's still correct. Or honestly, I can just hard code these. That's fine. This is negative 180. This is positive 180. Maybe that's easier to think about. So like if this is less than or equal to negative 180. I'll do the same for these. Negative 180. Positive 180. So if the turtle's x is less than or equal to negative 180, that means it's way over here. It's either like just touching the wall, grazing it, or it's outside. If it's outside, so either hit the left wall, or we're trying to go beyond it or something, go past it. Let's see here. This is supposed to be above, isn't it? Or we're trying to go past it, move the turtle back inside the left wall, so like change the x to be exactly negative 180 if it's more than that, or sorry, less than it. And then we want to change the x offset so we move to the right now. That's the trick. And that's the drawing that we had before. Like we were over here. If we try to go outside, bring them back in, and then also negate your x offset so that you're moving to the right and then in the same y direction this time. So if you hit the left wall or you went outside of it, make sure you go back inside, just touch the wall now, and then change the x offset so that you're moving to the right this time. Okay? So that's how that one needs to go. And then the last one is for the right wall. If we hit the right wall, that means our x is greater than or equal to positive 180. So let's copy and paste. It's greater than or equal to positive, it's greater than or equal to positive 180. we either just hit the right wall or we're trying to go past it. First of all, move the turtle back inside, make it exactly 180 if it's more than that, and then negate the x offset so that we move to the left now. So we don't want to keep going right, that's for sure. We want to bounce off, keep the same y offset, but like instead of going to the right, go to the left now in the x. And so that's how you can check for those things. All right. So technically, you could make this one an if and an elif, because you can't hit both the top and the bottom wall. And you could make this one an if and an elif, because you can't hit the left and the right wall at the same time. But you can totally hit the bottom wall and like the right wall. So you can't just make them all elifs. Okay, I'll just keep them separate ifs, it's fine. But those are the 4 real checks now that we needed. Any questions about these additions or why the existing ones still worked? So yeah, now every frame, move by your current direction in the x and y direction, and then bounce off if you hit a wall, and here are all our checks and our bounces. All right, so let's try this. Bounce off the top wall, we're doing that fine already. Now, moment of truth, nice. And this is just gonna keep going forever, and so it starts out. Let's see if I can walk you through it. Constant speed, as we normalize stuff. But let's see what we did. So we drew our bounding square, made the turtle a square, gave him a starting random spot, starting random direction, normalize that direction so that we always, regardless of the direction we pick, move at a constant speed, like speed 1 unit per frame each time. And then, while true, repeatedly draw a new frame. So like change, move in your current direction by your offsets, and bounce if you hit a wall. And that's going to change the x and the y, and this actually causes the animation to happen. So the turtle.goTo actually go to that new x and y that we just calculated from these things. And bouncing was all of these checks. If you went outside, come back inside, and go in the opposite direction now so that you move the other way. And so, yeah, maybe one day this will hit the corner. But every time you run it, it's a new starting place. It's a new random direction. So this one's a bit more horizontal in its direction. It's possible to randomly get perfectly horizontal, I guess. Then you never will hit a corner. But it's very satisfying. And so I encourage you to play around with like the speed of things. The speed is how fast you move in your direction each time. It's the offsets. So if you multiply these offsets by something, that will make it move faster each frame. Right now it's moving at a nice leisurely pace though. If I change this to be like times 5 after I normalize, then it's going to be 5 units each time. And that's going to be pretty fast. Whee! And so that is hard to even look at, but who knows? Maybe that's what you prefer. So, yeah, that's how that all works. Any questions about any of that? Definitely this is a good one to study, and it's a very satisfying thing to get working. And of course, I'll be giving you all this code. So that is that, I believe. Is that everything that I want to do for bouncing? Yeah, I think it works just fine. So that's that. And then let me show you my goal with this, because this is like, there's a reason I did the bouncing squares. Next, I would like to show you how to use the keyboard in the turtle library so you can like press a button and have things move. Because our goal is like, I would like to make a game for you. Our goal is Pong. Just like we did in Scratch. So we have the ball right now. This is a random spot with a random direction. That's perfect. Next, we need a paddle. So let's learn how to make the paddle. We want to be able to move a rectangle with the keyboard. All right? And that's what we'd like to do next. So we'd like to make Pong. And so if we want to make Pong, we need to get keyboard input from the user. All right? So that's going to be, there are some functions for that in the turtle library. It's down here. It's stuff about key presses. Let's see here. on key press and listen are going to be the ones that we care about. It's like on key press takes a function, and then which key we would like to call that function every time the key happens. Like it'd be like turtle.onKey, the up arrow key, put that as a string. That'll call this function called f that we define somewhere that does something like move up. That's going to be what we use. So on key press is going to be our friend. And we would like to make the paddle. So we have our little bounding square as usual. We would like to make a paddle like, I don't know, over here. And so we want the turtle to look like this. I'm going to use the turtle as the paddle again. And there's a way to make the turtle look like this. You can stretch the turtle. You can stretch the turtle in the y direction and the x direction separately. So like, apparently if you stretch him by 1.5 in the x direction and 6 in the y direction, it looks nice. Tried that before. The original size of the turtle is 20 by 20, and so if you stretch him by 1.5 in the x direction, that'll make him 30 by, and then 6 in the y direction, that'll be 30 by 120. That will be his new length. So let's get that working. Let's get the paddle started. Let's see here. I guess we can use what we started here, but I'm going to delete a lot. This time the turtle will be the paddle. And then we'll combine it later. So this will be paddle.py. All right, what do I want to change? I think I want to change a lot. So everything before all this. It's like draw the bounding square and then make the turtle a square. That's pretty much all of it. And now it's not a square, make the turtle the paddle. So, I don't know. Fill color can still be pink. Is width and height are going to be different now, but we can stretch him now. This is by 2 in the x direction and 2 in the y direction. We want to stretch him by, what was it? By 1.5 in the x direction and 6 in the y direction. So let's do it like this. 1.5 in the x direction and 6 in the y direction. So that will make him look like this. There he is. He's in a weird spot right now, but that totally looks like a paddle. That's good. So I guess the next step is like move him somewhere in the bounds of the square, like over here. Make him start there or something. And again, it's relative to his coordinates, so he's got to be like, I don't know, maybe his y coordinate can be 0, but his x coordinate could be like very close to negative 200 because that's over there. Something like that. So let's make, I don't know. Let's change it. Let's keep track of where the paddle is in some variables. Let's be like paddle x and paddle y. Let's start them at, let's make the y at 0 at least at the start, and let's make the x be like negative 175 or negative 170-ish. And that's where we'd like the turtle to move. So turtle.goto paddle x, paddle y. Maybe that's a good starting point for the paddle. Let's see if that works. Whee! That's not bad. But I said go to, and turtle draws lines if his tail's down. We never pick the tail up, so let's pick the tail up before I say go to. Turtle.up. And so that looks like a decent spot to start the paddle. All right. So any questions about how I got that? It's really just the stretching. That's really different. And then like picking a good starting point. But that is going to lead to the paddle for pawn. And now, the way that you can get input from the turtle is to say turtle.onKeyPress. And then that takes 2 arguments. You give it the name of a function that you've written somewhere else, somewhere up above, and then a string that represents which key you want to have that function called when it gets pressed. And so this is an interesting thing that maybe if you've programmed before you haven't seen before. It's you're passing a function to a function. It's kind of interesting. You can totally do that. Functions can be passed as to other functions. And then this onKeyPress is going to make fun get called whenever key gets pressed. That's essentially what's happening. And so we're going to make a function that will correspond to move the paddle up a little bit every time it gets pressed. And then another function that corresponds to moving the paddle down a little bit every time it gets pressed, the down key. So that's what we're going to set up. And then finally, after you call the on key press, that sets up the key press. And then finally, you have to say, turtle, I'm ready. I've set up all the key press events. Please start listening for the keys. It's like he can hear them or something. That's what it's called. Turtle.listen. Start listening to the keyboard, just to indicate that we've set up all our functions. We're ready to go. So here's how you do that. We want to set up functions to run every time the up and down keys get pressed. That's how I want to move the paddle when we do up and down. You can change this to like W and S or whatever you want, but we'll do up and down today. Keys are pressed. And so let's scroll this up a little bit. So I want to say something like this. Turtle.onKeyPress. The name of a function that I'm going to write, like, I don't know, go up. And I want that function to be called whenever I press the up key. And it's got to be capital up, apparently. And then I want to do the same for, like, when I press the down key. I'd like to call a function called go down, and that will be in charge of moving the turtle down a little bit. Just nudge him downwards. And then once I've set up my key press function calls, I say turtle.listen. And that just indicates to the turtle, I'm done setting up all these key press functions. I'm ready for you to start handling them when I press those keys. Please start listening for the keys being pressed. And so I need to make these two functions. They're going to be called when I press up and when I press down. That's just what we set up. All right? So, for example, let's do a go up function. Def go up. What do we want to have happen whenever we press the up key? Well, we want to change where the paddle's Y is, right? Y moves it up and down. So, like, I don't know. Let's use the paddle Y variable. Global paddle Y. It's got to be marked as global because it's a global variable, and I'm trying to set it within a function. And then what do I want to do the paddle Y? Well, I want the paddle to move upwards, so I better add some number, add some positive number to its current Y. Paddle Y equals paddle Y plus like 10 or something, I don't know. And then actually move the paddle to that new spot, because paddle Y is just a variable. It's turtle.goTo that actually puts him somewhere. So that's what I want to have happen whenever whenever I press the up key. It's going to call the go up function, which is going to mess with the paddle Y variable, and then eventually move the turtle to that new location indicated by the paddle Y variable. So here is, oh gosh. Oh, sorry, it gave me an error because I haven't done go down yet. Let's just say that go down doesn't exist yet. Let me comment that out. So there's my function. And now it's listening for my up arrow to be pressed. And if I press it, it's going to call that function. Boop. And that moves the paddle by 10 units. So we use the go to. If I press it again, up, 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 up. You can hold it in. And right now it can fly off the screen because we have no bounds checking. All right, let's do the same for down, and we'll fix it so that it never goes outside. So let's do go down. We want a function that gets called every time we press the down key, and we're apparently going to call it go down, go underscore down. And so this is like the opposite, like move the paddle by 10 in the negative Y direction every time you press the down arrow. It just calls that function every time we press those keys, or hold them in. Here I am holding it in. But again, right now, this can go outside of the walls, and that's not very cool. But it's starting to work. Any questions about this so far? Because the last piece of the puzzle is going to be make it so that it stops at the edges there. All right. See, in Scratch, you never had to deal with this. In Scratch, just like you couldn't let the Y get any higher or lower. It would just stop it for you. But nope, we got to be that check now for ourselves. So, all right, so we are here. What do we want to have happen? If we're at the top wall and we press up, we want nothing to happen at all, right? How do we notice that? There's going to be an if involved. So, okay. We want, for example, the Y to be, like the paddle should be up here at the very most. No more. And so what is the y coordinate of the turtle when the paddle is right here? Again, it's relative to its center. So it's really like you have to check for the y to be this value here. And so, all right, this is apparently 120 high. And so this, halfway there, is 60. This line is y equals 200. And so that means this center point, this y coordinate, that means we hit the top, we don't want to go any farther. That's y equals 140. 200 minus half the height, so 60. 200 minus 60, 140, and so that's the highest we could go. And I think you can likewise see that negative 140 is the lowest that we should go. So that's what we'll encode here. So we don't want to go to paddle y plus 10 potentially. Maybe that's too high. That's too far away. So make sure, before we even do that, before we go to, make sure we don't go past the top. So maybe paddle y plus 10 was past the top. We don't want to let that happen if that's true. So if paddle y is like 140 or greater than or equal to 140, that was too big, too high. Rein it back in to be exactly just touching the top now. Paddle y equals 140. It's either equal to or greater than, right? I guess technically you can say greater than only if you wanted to, but it makes more sense to me to use greater than or equal to. So if it's ever trying to go past the top, just rein it back in to be exactly at the top, no higher. Does that make sense? And then the same thing for the bottom. It's like, make sure we don't go past the bottom when you go down. The paddle y is trying to be negative 140 or less than that. Make it be exactly negative 140. Don't go farther outside the bounds. Just rein it back in to be exactly touching the bottom. All right? So that's how we want that to work. And it's very important that we do this check before, this resetting, before we say go to, because go to actually moves the paddle. We don't want to see it ever go outside. We're going to mess with the variables first, and the variables don't reflect reality until we say go to. So we can fix them up before that call. So that's why go to is very last. Once we have the right value, then we can say go to. All right, moment of truth. So pressing up, pressing up, pressing up. I am still pressing up. I'm holding up. Doesn't want to go any farther. Can go down though. But it doesn't want to go any farther than the top wall, and that was the right bound, 140. Negative 140 was the same. That was the right for the bottom. Right value for the bottom there. And so that is Pong in a nutshell. That's the paddle. We have the ball. All that's left is to hook them up. Are there any questions about this paddle file? So we just made some functions that get called every time a key gets pressed, and this was the style that the turtle library was looking for. And we had to have some more bounds checks because we don't want anything to go outside of our playing field that we've made here. All right, we're all good. Yeah, definitely study these. I think they're fun examples. I enjoy writing them, so I hope you'll enjoy studying them. And that is the end of the slides about 2D bouncing. We'll bring this all together and make Pong for real in the future. But the last thing for the day before we go is I need to tell you about your final exam. So we are right now in week 15. Week 16 is classes. Week 17 is the last week of classes. Week 18 is finals week. There's not normal classes. There's nothing on Monday. Our final, I'm going to release this final info page to you. And then eventually the exam will be there on finals day. You'll take it on Canvas, just like a midterm. Here is the final info. Apparently, if you look it up in the table for the campus, our final during finals week is the Wednesday. Starts at class time. So it's meant to be an hour and 50 minutes long, so it's slightly longer than our class time is normally. So you'll have that full time to do it. Our final will be from 4 p.m. to 5:50 p.m. on Wednesday the 17th. There is nothing on the Monday. That's just finals week. There are no normal classes. So don't show up here on the 15th. Just show up here on the 17th at 4. All right? And you'll take the exam in class just like you did for the midterm, and that'll be that. So that's the logistics. And then the topics are as follows. So I'm going to ask you an essay I'm asking you to write an essay just like you did on the midterm with a word limit of like 250 words or so, maybe a little bit more because it's a final. And then I'm going to ask you Python coding questions because I couldn't do that for Scratch, sadly. Like maybe you could screenshot something, I don't know. It wasn't really going to work for Scratch, but it totally works for Python because I can just give you a text field and you can fill in the text field with the program that I ask you to write. So prepare to write code and paste it into a Canvas text box. Get your idle set up all ready to go before the final. Understand how you want to do that. All right, so I'm going to take my questions from like the programming assignments that I've been giving you, and then all the example programs that I've been writing in class. If you study those, you should do pretty well on any of the coding questions that I ask you for. And then, for example, you should expect me to ask you about drawing something with the Turtle library. Expect to draw something cool. And yeah, so essay about non-Python topics, and then some Python questions to test your programming skills. The two halves of the class, so that makes sense that will be on the final. And so I promise to put at least the majority of the points towards the essay, because this is technically a critical thinking class that I want you to go out with a bang in your final essay of the class. And yeah, that'll be that. So the majority of the points will go towards the essay, but there will also be Python questions, and you'll type them up on Canvas. And just like the midterm, test is open book and open notes, so you can be looking at the code that I wrote in class as you're taking it. The only thing you can't do is talk to a human other than me. All right? So yeah, show up here on the Wednesday of finals week, and that's your final. Any questions about it? Oh yeah, totally. You can use your laptop if you'd like. Not a problem, because maybe you're more comfortable working in idle on there or something. Totally fine. Yeah. Any other questions? All right. That is all that I have for us today. The rest of the time is yours.